Hi, geometry students. Thanks for bearing with me through these days of videos and learning on your own. Thank you so much to the subs who've been there for you. So this is our last day of these videos, and we are going to start Unit 5 because I want to be there to go over the review with you one more time before we take our test on Unit 4. So we will do all the review together, go over any questions that you might have on Wednesday, and then we will take our test on Unit 4 on Thursday. So day 1 of Unit 5 is an introduction to transformations. So a transformation of a geometric figure is a change in its position, shape, or size. When you assemble a jigsaw puzzle, you often do this. You have to move the pieces around by flipping them, sliding them, or turning them. So this first jigsaw puzzle, we have to flip it over. The flip is called a reflection. When I slide my jigsaw piece, that's a translation. And when I turn it, I am rotating it. So a rotation. So these are our transformations. A transformation in a plane is a function that assigns each point of a plane to a corresponding unique point in the plane. The figure that is about to undergo the transformation is called the pre-image. The resulting transformed figure is called the image. So the pre-image happens first. It's the original figure you're given, and the image is the figure that we have after a transformation has occurred. A transformation is said to preserve distance if the distance between the images of 2 points is always equal to the distance between the pre-images of the 2 points. A transformation is said to preserve angles if the measure of the image of an angle is always equal to the measure of the pre-image of the angle. We're going to use this basic rigid motion term a lot this unit. And a basic rigid motion is a transformation that preserves distance and angles. Another way of saying that when you were in middle school was it preserves size and shape. So when I ask if something's a basic rigid motion, I'm really asking you, does it preserve the size and the shape? Does it preserve the distance, which is the size, and the shape, which are the angles? And we can abbreviate basic rigid motion with BRM. All right, so here's our first transformation. We're going to talk about a rotation. So you can see all these R's have been rotated. They all look a little different because their center of rotation is in a different spot. And they've also rotated a different number of degrees. So for a rotation, those are some things we have to know. We need to know the point to rotate the figure around, which is that center of rotation. We need to know which direction, clockwise or counterclockwise, to rotate it. And if you ever get mixed up with that, you can always take a look at the clock on the wall to see which way is clockwise or counterclockwise. And lastly, we need to know how far to rotate it, how many degrees. So after we consider these things, is a rotation a basic rigid motion? Does it preserve size and shape? Does it preserve the distance between the points and the angles? We'll look back at our example up here. Those R's look to be the same size and shape. So yes, it preserves it. So it is a basic rigid motion. All right, our next one is a line reflection. So these are all different line reflections, and you might be able to visualize where the line would have to be. I'm using my cursor to point them out. Just a little visual, a little sketch of where that line looks like it should be. And we're going to go through all of these transformations in much more depth throughout the unit. For a line reflection, we need to know where the line of reflection is, and we'll talk about how to find that. We need to know each image point is the same distance from the line of reflection as its pre-image point. So they're equidistant from that line of reflection. And then we also need to know the line of reflection is the perpendicular bisector of the segment connecting an image point and its pre-image. Wow, we've heard of that before, right? The perpendicular bisector, we've talked about that a lot. So if I go back up and look here, if I try to draw in one of these lines of reflections, I'm just going to sketch it in. Whoops, that did not go well. I want my line. There we go. All right, that looks pretty good. So there's my line of reflection. What this is saying is the line of reflection is the perpendicular bisector of a segment connecting an image point to its pre-image point. So if I take my line, I'm going to change the color so you can see it, and I connect from the tip of the R to the other tip. So that would be a pre-image and an image point. That red segment there, the black line is the perpendicular bisector of that red segment. So the perpendicular bisector is the line of reflection. Is a line reflection a basic rigid motion? Does it preserve size and shape, distance and angles? Yes. All right, a translation. This is the slide. So you can see all these T's have slid. They haven't been rotated or reflected. And for a translation, we need to have, whoops, we need to have how far to translate, and we need to have in what direction to translate. A figure is translated along a vector which has both magnitude and direction. All right, so hopefully that helps you remember that a vector has both magnitude and direction. So is a translation a basic rigid motion? Yep, it preserves that size and shape, distance and angles. All right, a point reflection. A point reflection does have the word reflection just like line reflection, but it's different in how it looks and how we find it. So here are some examples of point reflections. And like I said, we're going to go through all these in much more detail each day of our unit for Unit 5. But for a point reflection, we need what point the figure is being reflected through. And then, is a point reflection a basic rigid motion? Does it preserve the size and shape, the angles and distance? Yes. All right, dilation. This wasn't on our original list, was it? Well, if I look at my examples of dilation, I can see right away that my size is not preserved. So for our dilation, we need to know how much to change the size. This is called our scale factor. And we also need to know the center of dilation. So what point are we dilating in respect to? So is a dilation a basic rigid motion? Absolutely not. It does preserve the shape or the angles, but it doesn't preserve the distance or the size. So no. All right, so let's try just a few transformations with the reflection. So we have a triangle ABC, and we want to reflect it over the x-axis. So we have our pre-image points, A, B, and C, and I've graphed it for you. And now I want to reflect it over the x-axis. So that means I want to take each point, and I'm going to count them to the x-axis and count that same number of points down. So A right now is at -412. So if I go to the x-axis, that means I'm counting 12 units. Notice the scale is 2. So that means I have to go on the other side down 12. So for A, I have -4, -12. For B, B's way down here. It's at 2, -16. So if I count up, 16 up, and then go 16 again, that means B is on 2, +16. C is on the x-axis, so when I try to flip it over, it still stays there. So I'm on 8, 0. So back to my picture now. I'm going to make these points a little nicer looking, and I'm going to label them. So this is A prime. That little dash means prime, or the image. This one up here at 216, this is B prime. And then C and C prime are actually the same point. And now I'm going to take my straight edge. Remember, the side of your calculator works well. And I'm going to connect A prime and B prime, A prime and C prime, and C prime and B prime. And just take a moment to appreciate that that does look like triangle ABC flipped over the x-axis. So when we reflect over the x-axis, you should notice something that happens between the pre-image and the image points. So look at all of them, and what do you notice? You should notice that the x stays the same, but the y becomes the opposite. If this didn't happen for point C because it's on the x-axis, and notice if I tried negating 0, I still have 0. All right, let's take another triangle, and this time we're going to reflect over the y-axis. So let's start with D. Notice D is on the y-axis, which means it's not going to change. E, if I want to flip it over the y-axis, I count to the y-axis, and I count that many away. So there is E prime. And then F, I count to the y-axis and count that many over. And this is F prime. And then I better go back and not forget to put D and D prime are in the same spot. All right, so E prime is 8, 0, and F prime is -12, -12. All right, let's connect them. So F and E prime, E prime and D prime, and D prime and F prime. And that triangle EDF looks like it's been flipped over the y-axis. All right, notice what happened with my points. But this time, because I'm reflecting over the y-axis, the y-coordinate stays the same, but the x1 is negated. So negative x, comma y. All right, reflection over the line y equals x. This one's a little trickier to think about. But the line y equals x is the line that goes through the origin and has a slope of 1. Whoops. Let's see here. There we go. All right, so I want to see what happens if I flip this over. Well, one thing you might notice is that y is on y equals x. So that means this one's not going to change. For all the other ones, what happens? Well, can you visualize drawing in a line that would be perpendicular to my line of reflection, and then make it so that the line of reflection bisects it? It would look like this. So this is where x prime would go. Now it's hard to always visualize that, but that's what you're doing. And all I have to do is switch x and y. So if I look at z right here, z is at negative 12, 4. I'm going to go to 4, negative 12. And let's just draw on that line just so you can see it. So we got z to z prime right here. Let me just change its color so you can see it better. There we go. All right, so there it is. And now we have z and we have z prime. And now I can actually connect to show you that reflection. So if I go ahead and connect to make the reflection, I can do that right now. And remember, the 1 at y didn't change, so that's also y prime. And now you can see that this triangle right here looks like it flipped over the line y equals x and became this triangle. So down here for this rule, for a reflection over the line y equals x, we're going to take x, y, and we're going to switch them. They become y, comma, x. All right, 2 more examples here. If the image of P, 3, negative 1, over line M is P prime, 3, 7, write the equation of line M. In other words, write the equation for the line of reflection. So here I have P, and here's P prime. The line of reflection needs to be the perpendicular bisector of the segment connecting them. So in this case, because they're vertical, the segment's vertical, that means our line of reflection is going to be horizontal. So I'm just looking for a horizontal line. Whoops. A horizontal line that would be right in the middle and be perpendicular. So if I'm at negative 1 and I have 7, if I add those together, I get 6, and then divide by 2 is 3. And I can see that it is bisecting it. Here is the midpoint right here. So I've wrote my equation. Y equals 3. Of course, this can be more complicated when the points are not vertically or horizontally to each other. So let's try this one. Under a line of reflection, image Q is negative 1, 3, and Q prime is 5, 5. Write an equation of the line of reflection. So let's just do a quick little sketch. We've got negative 1, 3. And we've got 5, 5. So here is the segment connecting the image and pre-image points. And then just to estimate, my line of reflection is going to have to look something like that. So I can flip Q right over that line of reflection and land on Q prime. All right, to come up with this, I need to find the equation for the perpendicular bisector, and we've done this several times now. So let's start with the midpoint. Remember, to find the midpoint, I'm going to add my x's together and divide by 2. So that's 4 divided by 2 is 2. And then I'm going to do the same thing with my y values. So I'm going to add the y's and then divide by 2. So that's 8 divided by 2 is 4. So 2 comma 4 is the midpoint, and that looks pretty reasonable based on my sketch. All right, now I'm going to find the slope of Q prime. All right, to find the slope, I do change in y over change in x. And it doesn't matter which point I start with, I'm going to pick Q prime. So 5 minus 3, remember y is on top, over 5 minus negative 1. So that's 2 over 6, or 1/3. So then what is going to be the slope of the perpendicular bisector? Well, if I know 1/3 is for Q and Q prime, that segment, I'm going to take the opposite reciprocal. So that's negative 3 over 1, or just negative 3. All right, now I just have to put the point and the slope together, and I have my equation. So I can do point slope, which makes it very easy. Remember, y minus y1 equals the slope times x minus x1. So y minus 4 equals the slope times x minus 2. And there is my equation of my line of reflection. And notice I have that negative slope, which makes sense as it's tilting downwards. All right, so please do your day 1 homework for Unit 5. We will be doing day 2 of Unit 5 tomorrow, and then we'll switch back and we'll review for Unit 4. All right, have a great day, everyone, and I look forward to seeing you tomorrow. Bye.